Well, good morning, everyone, and welcome to this awesome four-part webinar series we're calling Getting Schooled by Siggy, with one of our industry's best-known teachers and PEs, plumbing engineers, John Siegenthaler. John's got a 35-year track record of passion for water-based engineering, and he's nice enough to share that passion with us here today and over the past 3 episodes of this month. I am your host, Dan Ashenden, group publisher of B&P Media's Mechanical and Plumbing Group, which includes our 3 well-known brands, which John, of course, writes for, some of them, and that's Plumbing and Mechanical for the contractors, the #1 contractor-focused brand, then PM Engineer, the leading voice for plumbing and mechanical engineers, and finally Supply House Times, the official publication and brand of the ASA, American Supply Association, and that's for wholesale distributors. This webinar series, of course, is brought to you by Caleffi North America with their outstanding hydronic solutions. And Caleffi has partnered here with B&P Media to offer you this complimentary webinar series presented by Siggy. So this series is the final one, as we mentioned, for the month of June, and this is it's designed to help you understand and design, construct, and commission hydronic heating systems that leverage today's low energy using technology while keeping things as simple as possible. After all, we all know that comfort and high efficiency equal a happy customer. So today's plan with the Getting Schooled series covers our final exam, is what we're calling it, with controls, performance, and lessons learned over the past few episodes. You will receive a certificate of attendance emailed to you for your continuing education efforts. So I think that's about covers most of the introduction. So without further delay, let's bring on Siggy. And we do have a special guest today with Bob Hot Rod Rohr, who's helping also moderate and ask questions and field your questions. And I think we're pretty much ready to go. Siggy, are you there?
All set.
Great.
Yeah.
And Bob, you there?
Yeah, thanks for the nice intro as usual, and glad to have everybody attending today. We've got a nice crowd and we've got a good topic, and I think you're all going to enjoy this. So a few housekeeping tips here. Yeah, the top paragraph there is mainly if you're having trouble, logging in, or you have a bad connection or bad audio or something. We usually recommend that you log out and log back in. That usually clears it up. But if it's an ongoing issue, there's a tech support number that you can get a hold of the folks at GoToMeeting and get some technical support there. This episode will be, in fact, that we've got a slide coming up, will be on our YouTube channel here in a couple days, so you can watch it again. I know when we get towards the end of this, Siggy, there's some schematic and stuff that get a little bit complicated. So also available will be the PDF of all these slides. So if you want to look those over and maybe play it again when we get to that slide, that'll be available. Give us a couple days to get those out to you. There's usually a survey at the end when you log out that should get a survey. Should come up on your email, then you can check there if you want the presentation, and we'll just send it right to send the PDF to your email. So yeah, that's a little bit about the topic for today. And let's see what else. I think we had a couple other housekeeping here, Siggy, and let's get going. Hydronics, hopefully everybody that's listening today is receiving the Hydronics, the hard copies, I should say. We're going to have the digital version of that for the first time ever for the issue number 27, and we'll show you a little sneak preview of that here in a second. But these are available. If you want to sign up for them, you can get the back issues also. And there's, yeah, I call it I-27. That's the issue that should be out here in July. A little sneak preview of what that'll look like. And it kind of ties into the topic we're talking about today, and I would imagine a lot of the slides and information will be in that issue that Siggy's going to show you today. So you'll have another opportunity to get to some of this information when that issue hits. Go ahead, Siggy.
Yeah. Well, thanks, Hot Rod and Dan. And since we're talking about resources, I just want to mention an ebook. This is a compilation of articles and columns from Plumbing and Mechanical, PM Engineer, and Supply House Times. These go back to 1996, so we're back 24 years. There's about 340 different articles that are covered over 5 different editions of this, and it's free. You can go to the multimedia link on the PM website, just scroll down and click on there, and you'll see ebooks, and you can look at that right on your screen. So there's a lot of information available to you, and it's completely free. And as Bob was saying, the Caleffi YouTube channel has an archive of the first 3 sessions. Again, today is number 4 of 4. So you can go to the Caleffi YouTube channel and take a listen to any of the sessions that you may have missed or just want to review from the past weeks. So
Hey,
today
Siggy,
yes,
let
go
me
ahead.
break in one more time, and we will have this Thursday is going to be a coffee with Caleffi, and it'll be I think a pretty unique and interesting one. Tommy Olson from Lochinvar is going to talk about the cogen unit that they've been offering and installing in different applications. So that'll be good. So mark that on your calendars if you don't have it. And that too will be on that same YouTube channel after we present that. So sorry to break in. Go ahead.
Oh, no problem. Topics today. Well, today's going to look at kind of a cleanup of other details that we haven't touched on. We're going to look at how we're providing domestic hot water in this system. We're going to look at a schematic, specifically a ladder diagram of the controls. I'm going to show you a spreadsheet that we put together to simulate the performance of the air-to-water heat pump system and show you how actually small changes in water temperature, for example, could have I'll say a significant impact on the seasonal COP. And then kind of the theme of all the sessions that we've been doing is when we take a look at the overall schematic, the piping schematic for this system, it appears to be complex, but what we've done over these sessions is we've disassembled that overall schematic into subsystems. And I'll go back and I'll review each of those subsystems, and then we're basically going to put them back together again, and you'll see how concepts like hydraulic separation allow us to put these different subsystems together and allow them to operate more or less independently and not interfere with each other. Okay, so let's start off with domestic water heating. We actually have 3 different heat inputs, or potentials for 3 different heat inputs for domestic water heating. The first one I'll mention is a de-superheater on the water-to-water heat pump. Now again, pointing at the water-to-water heat pump here, this is tied in with a closed loop geothermal heat exchanger. And when we ordered this heat pump, we ordered it with a de-superheater, which is a small heat exchanger that takes the hot gas directly from the compressor, and that hot gas passes through a portion of the primary side of that heat exchanger. The secondary side of that heat exchanger has domestic water passing through it. So we've got a pipe here. This is a 3/4 inch copper line coming from the lower connection on the water heater down. It goes through a stainless steel circulator that's part of the heat pump when you order it with the de-superheater. That circulator is already installed and wired. And that circulator operates whenever the compressor is running, with one exception, and that is if the domestic water temperature leaving the heat pump reaches above 130, it will temporarily shut that circulator off. So that's basically just an upper temperature safety control. So during heating mode, we're getting some heat transfer. Roughly about 10% of the compressor capacity is going into the de-superheater. But the part that's really nice about this is during cooling mode operation. Without a de-superheater, all the energy that has to be dissipated, the heat of rejection from the air conditioning system, would have to go into the earth loop. And our earth loop could handle that, but obviously once you've pushed that heat out into the earth, it's essentially gone. Well, with a de-superheater, at least a portion of that heat is being sent into your domestic hot water. So you're actually getting, especially during hot months when you run that cooling system quite a bit, you're getting a lot of free domestic hot water from that heat pump, simply taking heat that would otherwise go to the earth loop and putting it into that domestic water tank. So that's one option. Now, another option that we installed, since the geothermal heat pump doesn't run all the time, and since the system also has an air-to-water heat pump in it, we wanted the ability to transfer some of the heat that is produced by either of those heat pumps into domestic hot water. So we used what I call a sidearm heat exchanger, and this is a detail that's used a fair amount in Europe. And in fact, there are companies in Europe that sell the whole assembly that you can simply attach and pipe it right into the buffer tank. And this is a stainless steel heat exchanger. It's a flat plate, braze plate exchanger. The plate size is 5 by 12 inch, and there's 40 plates. So it's a pretty significant heat exchanger. The primary side is piped right off the top of the buffer tank, so that whatever water temperature is available at the top of the buffer tank would come down through the primary side whenever this small circulator down here is operating. And then the secondary side, we have cold domestic water coming in, and it's going up through the secondary side of the heat exchanger and absorbing heat from the primary side. And just point out, anytime you use a heat exchanger, you want counterflow. So always set up your heat exchangers for opposite flow directions. This is where you get the highest average temperature difference between the primary side fluid, the secondary side fluid, so you're getting the highest rate of heat transfer. Now, little details. You might be wondering, well, how do you know when to turn on the circulator? Well, we're doing it with a flow switch. And this is a flow switch. There's several companies that make these. They are rated for domestic hot water. It's a fairly simple little device, just a paddle. And I'll show you a photograph of it. But the contacts in that flow switch close whenever the demand for domestic hot water equals or exceeds 0.7 gallons per minute. So it's 0.7 of a gallon per minute. A contact closes, and we're actually sending that not directly. We're not putting line voltage directly through the flow switch. We're using the flow switch to activate a relay, actually a relay in a multi-zone relay center. And then the line voltage is sent by the relay contacts to this domestic hot water circulator. And this is just a small cast iron circulator. A couple other details you see here, that we have combination isolation and purging valves or flushing valves on each pipe connected to the secondary side of the heat exchanger. Again, that's the side with domestic water in it. And those are there to allow you to isolate the heat exchanger from the rest of the domestic plumbing and run a cleaning solution through the heat exchanger. Now, we're fortunate in this application that the water is soft. We don't anticipate we're going to get a lot of scaling, but that's not the case in many parts of the country. So one of the questions that does come up a fair amount about this detail for domestic water heating is, what happens if you scale up the heat exchanger? Well, bottom line is, if you've got hard water and you're not treating it, you're going to scale up pretty much any device that heats it. You're going to build scale in a tank. You would scale up a tankless water heater. So obviously, if you have water with high total dissolved solids in it, you need a treatment program. But legitimately, if there is some scale that does form in that heat exchanger, we've got a provision to run a mild acid solution through there, neutralize that, and flush it out. So that's the second way to heat it. And then finally, if I don't want to say if all else fails, but as a backup, we do have a 4.5 kW electric element in a standard, I think that's an A.O. Smith tank. It's a 38-gallon low-profile tank that I'll show you a photo of. It actually sits under a stair landing. So in theory, we could shut off, we could have the heat pumps off, nothing in the buffer tank. We still have 4.5 kW, which for the size of the house and the demand on the fixtures would handle it. And of course, we have our anti-scald valve up here to make sure that we don't send water above 120 degrees out to our domestic distribution system. So that's, again, quite a bit of detail going on there. And we put these subsystems together. Quite honestly, we can try different things with this. We can experiment with it a bit. In theory, we could probably say, well, we could eliminate this, and a more typical average geothermal heat pump would just have the de-superheater going to the tank plus the element. It wouldn't have this. But so say we wanted the ability to at least preheat domestic hot water with this heat exchanger. And we actually sized that heat exchanger so that the domestic water leaving that heat exchanger would be about 5 degrees, no more than 5 degrees lower in temperature than the water coming in from the buffer tank. So for example, if the buffer tank was at 90 degrees, we should still be able to get about 85-degree preheat. And then, of course, the preheated water would flow to the tank, and the element would take it to a final temperature. Okay, so here's
Siggy, you want to do a couple questions while you're on that slide? I had quite a few of them come in. The de-superheater will work in heating and cooling mode on that unit?
Yes, it does.
Okay.
Whenever the compressor is on.
All right. And then the flow switch, how does it decide on the that flow rate, the 0.7?
Well, it's actually what the manufacturer offers. One of the limitations on a flow switch is pipe size. As you go up in pipe size, and ours is a 3/4 inch pipe size, as you go up in pipe size, the activating flow rate has to go up. It's just a relationship of how the paddle and the flow switch works. Yeah. So we have a fairly small peak demand here. So a 3/4 inch pipe was plenty to supply the whole house, and that was actually the lowest set point for the on condition. Now, I will mention that flow switch, once it's activated at 0.7 GPM or higher, it stays closed until the flow drops to 0.4. So there is a bit of hysteresis built into that.
Yep. All right.
Okay, and let's see. Now, same schematic, just some photographs. Over here, here's the 38-gallon tank. Now, it's hard to see it, but we put the flow switch on the cold pipe, simply less stress on the switch than on the hot pipe. And here's a photograph that shows the flow switch. It's mounted into a 3/4 inch stainless steel T, and it just screws in there. And you, when you screw it in, you need to screw it in to the point where you orient the paddle. And inside that T, what there is a small little stainless steel strip that has a little some type of an engineered polymer disc on the end, and they engineer this so that the flow rate, obviously as flow goes past that paddle, it creates a drag, a force, and that's how they control the amount of force that is necessary to cause that switch to make contact. The pipes from the de-superheater, they basically tuck around around the back of the water heater. I will point out, we did put a secondary drain pan under that domestic water heater just because we do have livable space down in the basement, and it's all at the same level. So that is piped actually over to a sub-slab drain. If that water heater leaks, we have a way to catch that, and also the pressure and temperature relief valve would discharge into that as well. Now over here on the right, here's the heat exchanger. Again, that's 5 by 12 plate size, 40 plates deep. You can see the 2 isolation valves right here on the domestic side. Here's the circulator that is turned on by the flow switch. Basically, this is just the hot water from the top of the buffer tank down through the primary side of the heat exchanger. There's a check valve in that circulator so we don't get reverse flow if other loads are on. Purging valve on there, and then right back into our 2-inch stainless steel T that goes. Last week, folks, we looked briefly at this. This is the cooling provision, and we've got a 3-ton water to air air handler unit that's actually up in the it's within the thermal envelope of the building. It's actually up on the 2nd floor, and that can be supplied with chill water from the buffer tank. And in theory, either of the heat pumps, the geo heat pump or the air to water heat pump, can chill that tank down. Now, we've chosen to use the geo heat pump in cooling mode primarily because we have the de-superheater option. So again, rather than throw that heat to the outside air where we have no benefit from it, by using the geo heat pump with the de-superheater, a portion of that heat of rejection is going into the domestic water tank. So again, with a very minor change in some wiring, we could allow the air to water unit to chill the tank down as well. We did test it, it does work, but because of that de-superheater, we're favoring the geo unit. So here is a ladder diagram that we put together that shows the overall wiring on this, and we tried to keep this relatively simple, yet we try to also accommodate the control methods that the clients wanted. So we've got a ladder diagram, and if you're not familiar with ladder diagrams and you design hydronic systems, you really should learn how to use this. It's a very helpful tool. So we've got line voltage up here, and it's a 15 amp circuit, and you'll see this symbol right here. This is a normally open relay contact. Here's a circulator. So when this contact closes, we have line voltage going over to that circulator. Over here, we've got this is a Caleffi, I call them multi-zone relay centers, and you can see a photograph of it right down here. This is a 6-zone unit. This is set up for line voltage outputs. The normal application for this, it would have zone circulators on it. And you can see we do have circulators wired to some of the outputs down here, but we also have some other devices that were necessary here. For example, here's a line voltage zone valve that is turned on. Here's a mixing valve that operates, it needs to operate whenever circulator P8 is on, but this mixing valve requires 24 volts to operate. It's not a line voltage actuator. So we've got a transformer that is just wired in parallel with the circulator, and that transformer turns on whenever that zone is on, and we have 24 volts that goes to the actuator on the zone valve. We do have a couple temperature controls in here. These are Tecmar controls. This upper one is the heating control. That's a 2-stage set point control. And then the lower one is a single stage set point control that is used in the cooling mode. The junction box that you see here, this is a 12 by 18 by 4-inch deep, just metal utility box. That's where we put the relays, the transformers, just to neaten everything up, keep any line voltage terminals inside, away from where somebody could potentially touch them. Let's see, up here we've got, we actually got some really inexpensive thermostats that we put in. I think these thermostats were about $4 a piece on eBay. They're just a very simple little electromechanical heating only thermostat. We bought them just so we had something to operate the system with. At some point, we could easily replace these if the owners want to go to a more sophisticated thermostat. But we have that in the garage. We have that also in the basement. So you see a couple of those in there. The flow switch that we talked about with domestic water heating. The flow switch is actually wired to zone 6. We just arbitrarily chose that. It's not a priority zone. And that's what turns on the circulator for domestic water heating. The main floor does have a simple Lux thermostat. This is a heating and cooling thermostat. It has separate R terminals in it, 24-volt input terminals, one for heating and one for cooling. So you see schematically here, RH for heating, RC for cooling. And when we activate our heating mode, we get 24 volts out of the W terminal. When we activate the cooling mode, we get 24 volts from the Y terminal, which in this case turns on a relay. And you might say, well, why don't you just go directly from the Y terminal to turn on a heat pump? Well, there's other things that have to turn on. So we use the relays basically to integrate more logic, more specific logic to the system. And by the way, the relays that I've used for years, they're Dayton relays. They are triple pole double throw. And oftentimes we don't need to use all 3 poles on the relay, but I'm going to share a story with you in a minute here. It's always nice to have extra switching capability in relays. You may want to modify the system down the road. You may want to turn something else on. And literally for a couple dollars more, you're buying a triple pole double throw relay as opposed to let's say a single pole single throw relay. Over here, you'll see there's a switch. Again, briefly, we talked about this last week. This switch, this is a 4-pole double throw switch, okay? And what that does is it selects, we call it a lead lag switch. It selects which heat pump is the first one to turn on in heating mode. And right now it's set up so that the Geo heat pump can be the lead and the air source heat pump can come on if the buffer tank temperature drops a couple degrees lower than where it normally would be. But by flipping that switch, we can reverse that order. Now, there are controllers, there are two-stage boiler controllers that you could use that would automatically do this rotation, but we didn't really want to do this automatically. We wanted the ability to select which heat pump leads, not necessarily based on equal hours of operation, but for example, in the fall when the earth temperature is relatively warm, the GO heat pump is probably going to have the COP advantage. By spring, when the earth loop is cool, the air source would likely have the COP advantage. So we simply wanted the ability to switch that. So you see a photograph there of a 4-pole double throw switch. One of the things that I highly recommend, if you're using a switch like this, you'll see there's 12 screw terminals on it. You definitely want to put some pigtails on each of those terminals. Use some insulated connectors, insulated spade connectors, and give yourself like a 10-inch pigtail and put a tag on that pigtail with the number of the terminal on the switch. If you look here, you'll see the switch has numbers. They're very fine. You have to really zoom in to see them, but they're there. And this way, when you put that switch in the cabinet, instead of trying to work your hands in that cabinet and attach to terminal number 7 with a tiny little screwdriver in an awkward position, you can simply wire nut or use a compression connector to that pigtail. It just makes it go a lot easier, and it's also easier to trace that wiring if you're trying to troubleshoot it. All your terminals, all your pigtails are numbered corresponding to the switch. Now, we did run into something that was unexpected. We were getting some feedback. Originally, we were just breaking line voltage to the multi-zone relay center when we went into cooling mode. There was no need to run anything over there during, that was all the loads that are on the multi-zone relay center deal with heating. And we were getting some feedback, and the thermostat was giving us an error condition. It was seeing 24 volts on both RC and RH. I'm still not completely clear on why that was happening, but by installing another, by actually just using another normally open terminal on an existing relay, and again, that's the beauty of having that existing extra pole there. We were able to break both neutral and line. I think we were getting some feedback actually back through the transformer here. And we also put in another relay contact here that breaks. So basically we isolate that multi-zone relay center completely during cooling mode, and that resolved the problem. No issues. Okay. Again, our mode switch, and bear with me just one second. We're just going to move something here on my screen. Here's our temporary master switch, and you see it's temporary. It's just a couple toggle switches that we installed. There's been some paint on it. That's going to be replaced with a nice faceplate and a couple nice rocker switches. But that upper switch in the center position, the entire system is off. With the toggle to the right, heating mode is activated. With the toggle to the left, cooling mode is activated. And then the air handler, we set that up so that in cooling mode, the air handler would be on automatically. But if I want to do air circulation in the house, let's say when the system is in heating mode or the system is off, they just flip the switch over to on, and it connects across the low voltage circuitry in the air handler to enable air circulation in the building. So again, the wiring down here, these are specific terminals on each of the heat pumps. Obviously, when you get a heat pump, you're going to get a wiring diagram in the installation manual. And I won't say that these terminal designations match up with every heat pump. So if you're using a different make or model of heat pump, make sure you know which terminals, for example, which terminals turn on heating, which terminals turn on cooling. This particular heat pump had a 2-stage operation, so you see a Y1 and a Y2. To go to second stage operation, we had to enable both Y1 and Y2. So we had to put a little relay in. Again, here's an extra relay that's actually mounted right inside the wiring compartment in the heat pump. And that just, again, that gives us the specific switching logic that heat pump required to switch from heating mode to cooling mode. So again, I may be old school with relays as opposed to programmable controllers and so forth, but relays, you can do a lot of very customized control logic using relatively simple, very reliable. I think in all the years of using these relays, I've yet to have one of these relays fail to my knowledge. And they're inexpensive and they're versatile. So that's the overall wiring diagram. Again, here's a photograph of the 4-pole double throw switch there. Okay. Now, on this system in heating mode, when the thermostat, or I should say the mode switch is set to heating, it turns on this small Taco 0018 circulator. This is set up on, right now it's on a constant differential pressure mode. And one of the nice things about this circulator, it's Bluetooth enabled. So you can actually you download an app on a phone, and you can actually turn on the circulator and see exactly where you're operating from a flow rate and head standpoint. You can get the flow rate, and you can also get the wattage. So I did some experiments with this. When we operate with all the zones turned on, we got up to 4.3 gallons per minute, and the wattage input to that circulator was 27 watts. So if we're operating on a 20-degree delta T, and I didn't actually measure this, but this is a typical design load condition, a 20-degree delta T, and we have 4.3 gallons per minute, we have enough water flow to move 43,000 BTUs per hour. Now, this house doesn't require 43,000 BTUs per hour, but perhaps another house with higher load could. So the point I want to make is that we could move 43,000 BTUs per hour on 27 watts. So we calculate what's called a distribution efficiency, and that's simply what's the rate of heat transfer that our distribution system is giving us, divided by the necessary input power to run the distribution system. In this case, it was just the 27 watts going to the circulator. So we get this number here, 1,593 BTUs per hour are being moved from the mechanical room to where it's needed in the building per watt of electrical input power. And that's actually pretty good. And just for a comparison, I looked up some operating data for a 4-ton geothermal water to air heat pump. And again, I want to emphasize water to air. It's a geothermal loop going to a forced air distribution system. And that particular heat pump used a ECM, a 1 horsepower ECM blower, and at full power at 48,000 BTUs per hour being delivered at 746 watts. Take a look at the distribution efficiency. You can see it's down quite a bit. It's a small number compared to the distribution efficiency that we're getting. And just to put those two in perspective, this particular system is moving heat using about 4% of the electrical input energy that the heat pump, the forced air side of the heat pump requires. And it's not a put down on a geothermal heat pump. It is showing you the difference between moving heat using water versus moving heat versus using air. You have to move a lot of air because air has a very low specific heat and a low density, and that simply requires a lot more electrical input power. So it's just kind of a spin back to one of the fundamental advantages of hydronics, the vastly superior distribution efficiency. Now, Bob was mentioning that there's some slides here that if you really want to study this, you'll get the PDF file and you can read through it. Over here on the right, you'll see a lot of text. And what this is a very detailed description of operation of the entire system. It's basically a narration of what we just talked about, but it refers to very specific components on both the piping schematic and the electrical schematic, like P1, P2. or valve 1 or transformer X2. And the reason for writing this is so that a technician that didn't install the system, not familiar with the system, perhaps it's 3 o'clock in the morning on Christmas Eve and there's something wrong. Here is a written description of exactly how that system is supposed to operate with detailed references to specific components. And it's the starting point for troubleshooting. You read through for example, how does the lead lag switch work, or how does the heating cool mode switch work? It allows somebody to understand what the designer's intended operation for this system is. I'm a firm believer this should be done for every hydronic system, and it simply gives you value to your customer, because obviously this is a customized system, and 20 years from now, maybe I will be available to walk next door to my daughter's house and troubleshoot something that's gone wrong. So we want to make sure we leave a roadmap on these systems. Okay. Now, I mentioned a performance simulation. We put together a spreadsheet, and again, you're looking at a lot of numbers that really you don't have to look at all these numbers, but I would like you to look at this number right down here. That is the seasonal average coefficient of performance based on the performance curves, in this case for the air to water heat pump. And when I say performance curves, we have curves that give the heating capacity as well as the coefficient of performance. And both of those are functions of air temperature outside, and they're also functions of the water temperature that the heat pump is producing. And in Hydronics 27, again, coming out next month, we show you how to do that model. We're using something called a polynomial, a second order polynomial, to model. And that's really just an equation that describes a curve. You could get this curve from the literature or the spec sheets on this heat pump, and you can basically fit an equation to it. And the spreadsheet basically just uses that equation along with weather data. And in our case, our closest detailed weather station was Syracuse, New York. So over here you see bin temperature data from very cold to basically where no heat is needed. This is the number of hours in an average year that the air temperature is within plus or minus 2.5 degrees over this number right here. Now, on this particular spreadsheet, we ran this where the average tank temperature was 105 degrees. We did not use outdoor reset control. We also put in some limiting factors. And one of the things you have to be careful of with models is that at both ends of the spectrum, the model can either overpredict or underpredict performance. We limited our model so that under no case would we allow the heat pump to have a coefficient of performance over 4.5. Now, that was just somewhat of an educated guess on my part. It is possible that that heat pump might get up to maybe 5, maybe even 5.5, but that would be under conditions where, quite honestly, there's very little heating load in the building. So rather than allow those to kind of skew the data a little bit, we limited our COP to 4.5. And same thing on heating capacity. In theory, we probably could get a little bit higher heating capacity if the temperature outside was, let's say, 58 degrees. But the house that this heat pump is in really doesn't need any heat at 58 degrees. There's enough internal heat gain to provide any load. But what I want to show you is that when we model this system where the buffer tank swung between 100 and 110 degrees Fahrenheit, those are just the set points on that set point controller that turn on and turn off the heat pump, our seasonal projected coefficient of performance was 2.75. Now, interestingly, with a spreadsheet, I just changed that. I lowered the water temperature by 5 degrees. So we're swinging now between an on temperature of 95 in the tank and an off temperature of 105. The COP projection goes up to 2.9 or 2.92, which I thought was kind of interesting. A 5-degree drop in water temperature, getting us, pretty close to a 3.0 COP, which is a reasonable number for a geothermal heat pump. And then one other thing we tried with the spreadsheet is, let's say we just use outdoor reset control on the tank. In other words, we never heat the buffer tank warmer than what we need for the prevailing heating load. The COP increases to almost 3.5 under that. So we're taking advantage of those partial load conditions. We're significantly reducing the water temperature the heat pump is operating at, and we're seeing that reflected in the COP. Now you might say, well, why didn't you just run it on outdoor reset? Well, remember, we're also trying to do domestic water heating. So the trade-off is, yes, if we run it on reset, we're going to get higher space heating COPs, but we're starting to lose the preheating effect on domestic water. Somewheres there's an optimal point. In all honesty, I don't know where that optimal point is. We may experiment a little bit with it, but I did want to show you that the water temperatures that you're running the heat pump at do have a significant impact. And the other thing is, these are COPs that are in the range of what water-to-water geothermal heat pump systems are producing. They may be a little bit lower, maybe 0.5, something like that, but again, an air-to-water heat pump is a substantially less expensive installation than a geothermal heat pump. So I want to show you this new generation of low ambient air-to-water heat pumps is starting to produce performance numbers when properly applied in low temperature systems that could rival the numbers of geothermal heat pumps. And then finally, we did a quick comparison. And again, bear with me, I have to move something on my screen here. What we wanted to look at here was comparisons between energy costs on $1 per million BTU basis. And where we are, where this house is, there is no natural gas available. So the choice would be propane. And a couple months ago, propane was about roughly $2.50 per gallon. And that works out, if we were to run that through a high efficiency boiler, it works out to about $29 per million BTUs. Fuel oil is available. The price is down. It actually got a little lower than this during the point there where I think that was the petroleum futures were negative at one point. I couldn't quite wrap my head around that, but I guess that's good if you're an investor, bad if you're an oil company. But at $2.23 a gallon and 86% efficiency, figuring through a modern oil burner, about $18.50 per million BTUs. Now, let's compare that. Our local electrical rate this spring, just a little over 9 cents a kilowatt hour. So if we ran that heat pump at 9 cents a kilowatt hour with a seasonal COP of 2.75, and it was based on keeping the tank at the warmer temperature under set point, you can see at $9.66 per million BTUs, we're substantially less expensive than either fuel oil or propane. And finally, if we were to run the heat pump on outdoor reset control, where our seasonal COP was 3.47, we're even lower, $7.66 per million BTUs. So this is a very realistic option, and we have electricity at, I'd say, probably an average price. I'm sure there are areas where electricity costs, probably twice as much as that in the United States. But it allows you to do a comparison. In our case, with the local prices and the COPs that we're running the system at, we're actually doing quite well in terms of dollars per million BTUs delivered. And again, in Hydronic 27 coming out in July, we do have more information to show how that spreadsheet is put together. It's basically just putting some formulas in there to model COP and heating capacity and combining that with climate data to figure out where this heat pump is running and for how many hours over each of these temperature bins. Okay. Now, lots of subsystems. We've talked about pretty much everything here. And what I did, I took that overall schematic and just broke it apart. And I like to do this because, again, people get a perception when they look at a schematic that, wow, it looks complicated. How does the water know what to do, where to go? But when you take it apart, you can see these individual subsystems. The air-to-water heat pump is basically an outdoor unit, an indoor unit. a refrigerant line set, and a hot and a cold pipe that connect to a buffer tank. The Geo, little more hardware there. We've got the earth loop, expansion tank, circulator, air and dirt separator, and the heat pump itself. But again, it interfaces to the buffer tank with a hot pipe and a cold pipe. So basically these two sources just plug into the buffer tank. And again, I've left some of that piping there. Check valves to make sure we don't get reverse flow when one heat pump is running and the other one is off, and purging valves just to help us get the air out of the system. The buffer tank is actually providing hydraulic separation as well. That's why I've tried to emphasize the headers that we're working with on the buffer tank. We use those 2-inch stainless steel T's and some close nipples to put them together to create what I kind of affectionately call a short fat header. We want very little pressure drop in that header. And when we combine that with very little dynamic pressure drop in a buffer tank, we have the necessary underpinnings of hydraulic separation. So the buffer tank, in addition to providing the thermal mass to prevent short cycling, it's also providing hydraulic separation, not only between the two heat pumps, but between the other loads that are on the right side of the tank. Again, we had basement heating with a mixing valve. Okay, very standard. We used outdoor reset control to operate the mixing valve. Here's the garage slab that was using a heat exchanger with antifreeze, so that if the owner does not want to heat the garage, just to save some energy, they can completely shut that zone off and not worry about anything freezing. We talked about the domestic water today. Last week, we looked at the distribution system here, a combination of panel rads and some floor circuits. We're using a zone valve in one case to operate all this as a single zone. And then we're using thermostatic valves, thermostatic operators to operate the panel rads and towel warmer and a couple floor circuits. And basically, these are just a couple home run systems tied into a common set of piping that in turn ties back to the header. It's the load supply and the load return header on the buffer tank. And then the last one was the chill water detail, where the buffer tank supplies the 3-ton chill water air handler. So again, those are all the pieces. There it is, just pushed back together again. And again, I'd emphasize, if you're working with schematics, if you're new to hydronics and you're looking at schematics like this and it looks very confusing, learn the basic concepts, like how do you do parallel pumps. When you do parallel pumps, whether it's for the two heat pumps here or whether it's for zone circulators, you have to have a check valve in each one of those circuits to make sure you don't get reverse flow. That sounds very simple, and it is simple, but it's a very fundamental concept when you put these systems together. So is hydraulic separation. So is counterflow. When you put a heat exchanger in, always make sure the flows go in opposite directions, okay? Always make sure you've got purging valves in there on each of your subsystems, just to expedite getting that air out of the system. Make sure you have provisions, obviously, for an expansion tank, makeup water. Make sure you have isolation flanges on all your circulators and so forth. So, those of you that have worked with hydronic systems, these are all the very fundamental concepts. Those that are new, these are the things that you learn to almost instinctively put into your schematics as you put them together. And we're getting close to the last slide here. So I just want to show you a few more details. We tucked our makeup water system here under the stair landing. Here's the expansion tank for the system. That's a pretty good size expansion tank. I think that's I believe that's either a 9-gallon or 11-gallon tank. I think it's the largest tank that we could get hanging, and we needed that because we've got, in addition to the water that's in the floor circuits and the panel rads, we've got a 119-gallon buffer tank that's going to swing through, not a huge temperature change, but reasonable. When we put the hardwood floor down in the areas where there is floor heating, we searched till we found a mastic that could, without any question, handle the temperatures. And it was interesting. We looked at several different mastics. We wanted a good bond between the underside of that floor and the OSB subflooring to enhance heat transfer. But in looking at several of these mastics, we found that several of the temperature limitations. Here. Hi, Rock, can you hear me now? Hello?
John, we can hear you.
Yes.
Oh, okay. I'm sorry. The mic just, I actually stepped on the mic cord, disconnected it there for a minute.
Okay.
Murphy's Law, I guess, right on the final episode. Anyway, we found several mastics that were not rated over 85 degrees, and I still have a problem with that. How do you put a mastic that is not supposed to go over 85 degrees into a house? Actually, it's 93 degrees outside yesterday in upstate New York. Does that mean that the warranty on that mastic is voided if there's no cooling in the house? So we found a mastic. I think this was particularly rated up around at least 140, 150. Now, we're not going anywhere near that temperature. The water temperature going out at most here is 110 degrees. But we wanted to make sure that this wasn't going to outgas, that it had temperature specs that were conducive to what we were using it for. We did use a magnetic air and dirt separator as the main separator on the system. Again, this is just a detail. This is actually the heat exchanger for the garage. That's a 5x12 by 30 plate exchanger. Here's a double purging valve to fill it and get the air out. Here's a separate expansion tank for that. Today we looked at our controls. Again, there's a Caleffi multi-zone load center, our relay cabinet, a couple Tecmar set point controls. This is our master switch. Turn that switch off, you kill power to everything. On the top of the domestic tank, we used a anti-skull valve here, and we also, here's the flow switch. This is the P&T relief valve. Last week I showed you that detail. That's an H-pattern dual isolation valve that goes under the panel radiator. So if that radiator has to be removed for any reason, we just take a screwdriver, close these off, and open the unions up and pop the radiator. Here's my short fat header. Harvey put this together really well. This is actually a 2-inch stainless steel cross and a couple 2-inch stainless steel T's, and you'll see reducer bushings in there to get us down to the pipe size. And you'll see our purging valves near where each of these load circuits comes together. And then finally, we used a T-drilled copper manifold for our domestic plumbing. And a little hard to see it, but there is a Dahl mini ball valve on each one of these connections, so we can individually shut off hot water or cold water flow to any of those fixtures. So, all right, now we've had, over the past few sessions, we've had people jump in with answer very, very quickly. So this is going to be a little bit more challenging. Today, to win the t-shirt, you have to answer both of these questions correctly. Okay, so we're going to give you a little bit of time on this. So here's the first question. What flow rate of domestic water was required to close the flow switch? Everybody remember that? There was a switch that closed at a certain value. And I'm going to give you a hint here. It starts with a 0 point. All right, so that's the first question. 0 point, you fill in the blank. And then the second question, I showed you a switch that was used to determine which heat pump was the lead and which was the lag. How many poles, how many independent pathways through that switch were required in order to get that logic? Okay, so it was we're looking for a number of poles, and I will tell you it's a double throw switch, but how many poles were required? So Mary, I'll let you monitor answers to those questions. And while that's going on, I just mention again, tech support team out at Caleffi, tech support email. So if you've got questions on product application, these fellows will help you out. And I also want to mention coming up on in July, actually a month from today, July 23rd, we're going to do a coffee with Caleffi, and it will be centered around the topic for the next Hydronics, number 27, which is air-to-water heat pump system. So you'll see more detail on what we've talked about in this system, but a general discussion of air to water heat pumps. How do they compare with other types of heat pumps? And several complete template designs for heating only systems, heating and cooling, and domestic hot water. Oftentimes that's how we do our final section in hydronics, is we take the information from the initial sections and put it together in a form of several different templates for systems. And Bob, I'm going to go back to you if we've got some questions while those quiz answers are coming in.
Yeah, there was quite a few, and I got to a lot of them, but let me ask a couple that I didn't have the correct answer for, possibly. What the software program you use to do your schematics for the wiring, I guess, is it the same one as your mechanical schematics, or how do you do those?
Yeah, it's a program called PowerCAD. It runs on Mac. I've used it for years, and like many things, you get very familiar with it, so it becomes almost second nature to do the drawing. But in all honesty, anybody that doesn't have CAD software, if you simply go online, Google free CAD software, there's several companies that have software that could do any of the drawings that I've shown you here. So I just happen to use PowerCAD because I'm familiar with it and have used it now for quite a few years.
And we have quite a few stencils available too, Siggy, on our website that could be used in Visio and other programs with a lot of those boilers and different things that you showed today. I think you've built stencils for us too.
Yep. And you know, a quick plug here. I've been working with some others over the last couple of years. We've got a program called Hydrosketch, which is a cloud-based program, and that's specifically designed for constructing these schematics. If you want to try it out, just go www.hydrosketch.com, and there's a 30-day free trial. You can download it and play around with it.
Yeah, that's a great one. Yeah, I forgot about that. Thanks. And then Derek asked if you could share the name of that mastic. I guess he's struggled with getting the higher temperature mastic. Do you know the brand of that by chance?
You know, I'm going to have to look that up.
Okay.
I'm going to have to look that up. I think, yeah, I don't want to say. All I can tell you is that we did get it. It came from either a Lowe's or a Home Depot.
Oh, okay.
And it was a major brand, and the stuff is not cheap. It's about $130 for 5 gallons.
Thanks.
But and a little detail there too. We found that initially we were putting it on the floor and then putting the boards down and tapping the boards together with a block and a hammer. We actually found it went a lot faster if we simply put the mastic on the back side of the wood and then put it down. Small difference, but it did make a difference in just the ease of application.
Okay, well, thanks for the install tip. Drew had a good suggestion, putting all your schematics and stuff on a cloud too, for somebody to access down the road. So if the drawing got lost or something, they'd be out there for eternity, I guess, if you put it up on a cloud.
Yeah, and you know, just again, a quick disclaimer. You know, the schematics that we're showing here, these are, you know, specifically for this system, and there's definitely concepts that you can pull from these schematics and reuse again. But you know, I certainly don't want to say, you know, duplicate this schematic in exact detail on every project. It's a matter of understanding, you know, the concepts that these subsystems represent, and you know, once you get that, you can put together virtually anything that you need. Which is one of the things that's always fascinated me about hydronics is how versatile it is. And you know, this project was a good test of that. There were a lot of very specific and unusual characteristics in this project, and they were all accommodated with the hydronics.
Okay. Yeah, thanks. Somebody asked about the home run domestic water piping. No way to put a recirculation on that, really. I think that's the key to it. You just have short runs where you typically don't need recirculation on the hot.
Yeah, that's kind of the trade-off. We kind of debated back and forth between 3/8 tubing and 1/2-inch PEX on the hot and cold. We ended up using half because we do have a well pump, and we have the well pump in theory running between 40 and 60 psi, which is plenty of pressure. But with a 3/8 line, you do get a faster purging of cool water in the hot water pipe, and quite honestly too, I think the longest distance from that manifold to any fixture is on the order of 20 feet.
Oh, yeah, that's no
So
problem.
it purges out pretty quickly.
Yeah. Let me see what else I had scrolling through there. I think we've got pretty much all of them, some requests for some slides and stuff, which will be available at the, when you get the survey. If you check that, we'll send you the PDF of that. Somebody asked about some high res photos. We'll get back to you on that if there's something that they had in mind specifically. I think pretty much got the questions, unless Mary had, I didn't see any hands raised or anything going through it, so I think we might have covered certainly anything.
Well, you know,
the question we will
we
get
didn't
to.
have, oh, I'm sorry, Bub. We didn't have hands raised, but John, I think you did a really nice job with that question, or the two questions. And we have a senior mechanical engineer named Michael Levine who has had the answer of 0.7 for the first question for your domestic hot water to activate the flow, and 4 poles, if that sounds correct.
That is correct. Very, very good. Good paying attention.
Yeah, congratulations, Michael. We'll get you that T-shirt. And to everybody, we appreciate it.
That's great.
Do you have a new another version of Modern Hydronics? Will we be coming up with a new version of that?
Yeah, that's actually being written this summer. Well, it's being written from, takes about a year to write it. It takes another year for the publisher to put it together. And one thing I have found out, although I don't have final dates on it, given the COVID situation, it's changing schedules a bit. So I can't guarantee when it's coming out. The previously scheduled release of the 4th edition would be January of 2022, which seems like a long ways away, but that is being developed. It is going to have definitely more information on renewables in there and low temperature systems. So yeah, working on it, and the writing will probably be done by the end of this year. As I say, it'll be at least a year before it'll be out.
Okay, I think so. What's the most recent then is with renewable energy, heating with renewable. I think that was probably your most recent, although that needs to update too. I guess almost every year you need to update with the equipment that's coming at us these days.
Well, it changes a lot. You know, for example, the solar thermal market changed a lot. We see, and I can tell you as an author, it's true about pretty much any book you'd write. By the time the book is out, there's especially on technology, there's always new stuff that you just simply don't have time to include. So we get it as up to date as we can and go from there.
Yeah,
that's the beauty of webinars, right?
True.
Or also print on demand books too, where you can get them out, almost immediately, or digital, get them out. Yeah. So yeah, anybody else on call? I think we wrapped it up at a pretty good time. Sorry about the breakdown there for a few minutes, but it looks like pretty much everybody got back on. So
Hot Rod, I was just going to say we had a celebrity attendee in listen mode only, to Dave Yates, same contractor from the Northeast there, and he said he was going to be typing some questions, and I was texting with him, and he said, boy, I don't have any questions. All was covered perfectly. So that's a great testament to you, Siggy.
Yeah. Okay. And I know we did have somebody ask about the mastic, and I will get that. So whoever asked about that, just make sure you put that question in, and we'll follow up with an answer on that. I'll get you the brand and specifics on that mastic.
Yeah, that's Derek up in Chicago. We both know him, so we'll remember to find you up there and get you that answer. One last question, David Smith. I think he's a local engineer here, about mixing stainless and copper. Any issue with that?
No.
I guess that's on the closed loop side of it, wasn't it?
Yep. Yeah, it's closed loop, and no, we haven't had any issues actually, even in potable applications. I mean, a stainless steel heat exchanger connected to copper tubing, not any issues with it.
Okay. Well, I'm good. If you're good, everybody else, all the other organizers and people online, feeling good about this? I think it was a great series. It was certainly a timely topic. A lot of people looking at this, and like I said on the beginning, more manufacturers are coming out with this equipment, so there's more choices, more sizes available. Certainly going to be more training on it, and watch for the next Hydronics, which again we talk about a little bit more detail there. So yeah, we'll keep bringing the information that that the industry needs or requests. So let us know what we can do to help you out there for both upcoming webinars, also Hydronics that we've got coming up. We're always looking for interesting and new topics for those too. So thanks for everybody's support and input over the years, and we'll keep the machine running, Siggy.
Thank you very much for moderating. And Dan, thank you. And Mary, thank you as well.
Yes.
Yep, great job.
Great job.
Great job, John, and also Hot Rod and Mary.
Mm-hmm.
Oh,
Thank
there
you,
he is.
audience.
All right. Excellent. Thanks, guys. See you soon.
Yeah. Bye-bye.
I know.
All right, thanks everybody. See you on the next one.